Now I'd like to show you how you can use this result to derive some rigorous theorems about the behavior of the electric field. I'd like to emphasize that this analogy here that I'm drawing between, once again, the electric world on this side and the water world on this side is fully mathematically rigorous, because we've made sure that we have exact equality between our point sources and our point charges, and we are obeying the principle of superposition. So you can take what we're about to say really as rigorous derivations. So let's take a look then at some fluid questions that we can answer with our fluid intuition that then will turn into important theorems about the electric field. So while I'm asking you these fluid questions, I want you to think also what the corresponding electric questions are that we'll be asking and answering momentarily. So here, let's ask some questions about fluid flow. So some fluid questions. So first, we can suppose that I'm going to have, one of my famous hoses here, right? And he's going to have my famous little point source down here, and I'm pumping current I down that hose, down towards that point source. And I'm going to ask about what happens if I were to integrate the charge density times the velocity field dot dA for a certain surface. But now, rather than just taking, say, some spherical surface, I'm going to make a more complicated surface. I'm going to have a surface, I'll add another bulge to it over here. So I'm going to make this kind of like a peanut type shaped surface. What would happen now if I were to integrate rho naught V across that peanut type surface? What actually should I expect to get in that case? Well, from our fluid behaviors, we recognize that rho naught times V, right, is the total flow, it's the current density J. And I also know that whenever I integrate J, current density, dot dA over a surface, I get the total flow through that surface. Now, I'm being very careful here, actually, to integrate up over the entire peanut. So let me make sure to emphasize I'm talking about a closed surface integral. And I don't like how my peanut diagram came out. Let me just erase this here. That looks a little bit more like the peanut, right? It's a three-dimensional peanut, and I'm pumping current basically into one side of the surface. Well, because now it's a closed surface, and I know that the flow in must equal the flow out by conservation of mass, I know that the total flow out of this peanut surface must actually be the current I that I'm pumping down into the surface. And the neat thing about this result, I think you'll notice, is that this result is the same I would have gotten if I had taken the sphere, right? But now I get it for some completely general shape. So that's the first thing I want to emphasize, is that the result is shape independent. Well, that's kind of neat. Now, let's try another fluid question. So in this case, once again, I'm going to have my little point source, my little sprinkler ball, and I'm going to be pumping my current I down my hose once again. And once again, I'm going to inquire as to the integral around a closed surface of my density times my velocity. But now what's going to be different is the peanut surface, which is sort of my favorite general crazy shaped surface. Here's another peanut surface. The peanut surface is going to be over here. It's not actually going to have the source within it. What is it that I should expect to get in this particular case? Previously, when it was inside, we got the current I. What are we going to get now? Well, if we think about this a moment, it's a little bit tricky, because I know that my sprinkler ball here is going to generate, some kind of flow pattern outwards away from my sprinkler ball. And that flow is going to come into, one side of this peanut. But the thing we notice is that it's going to also be coming out the back side of the peanut. So what's important to notice here is that the net flow out of my surface, which is what this measures, is going to be 0. What will happen is on this side of the peanut, you'll notice that if I look at my area vectors, they always point outward from the inside of my surface. I'm going to have on this side, I'm going to have dA pointing this way and velocity v pointing that way. So the angle between those will be 180, and in that case, the cosine of the angle, cosine 180, would give me a -1. On the back side of the peanut, we have a different situation. On the back side, dA points out that way in the same direction, general direction as the velocity. I would get cosine of 0, or actually a net positive outflow. So this measurement tells me the net flow through the surface. So that gives me, if I want to call it, net current. But the net current, because in must equal out in a steady state flow, and whatever's coming in, everything that comes into this peanut's coming out the back, that means that the net flow has to be 0. Okay, good. Now, there's a third scenario that I would like us to analyze in the fluid case before we get to the electric questions. So in this scenario, what I'm going to have, a third scenario, I'm going to have, once again, my favorite peanut type shape, like so, right? Something like this. And I'm going to have actually a series of point sources. I1 here, where, I've got a hose connected to that guy. Another one, I2, on this side of the peanut. Maybe on this side of the peanut, I've got I3 being pumped in. And also, I don't know, I might have some other sources sitting around out here. I might have I4 that is outside the peanut. It's got his hose here, of course, connected. And I don't know, down below the peanut with his own hose, an I5 being pumped in to that point. What now should we expect the integral of the density times the velocity to be over this surface? Well, remember, we're measuring the net flow out of our peanut, and we know that flow in must equal flow out. So what we have to consider then is what is the net flow into the peanut surface, which then will balance this net outward flow out of the surface. Well, I4 and I5 are not actually pumping fluid into the peanut, right? They might create flows that go in one side and then back out the other, right? But they give no net contribution to be what's being put into the surface. What's being put into the surface is just I1, I2, and I3. So then, therefore, I know that this integral will give me I1 plus I2 plus I3 with no contributions from the outside sources, which are not pumping fluid directly into the interior of the peanut. Okay. So now it's time for, that kind of makes sense, I hope. So now it's time, though, to ask corresponding electric field questions, something about which before this discussion we might not have had, very strong intuitions. But now let's see what we can do. So for the electric questions, I'll begin with the same thing. Suppose now I'm given a peanut shape here, and I've got a charge plus Q sitting here in the center of this side, but now it's not a perfect sphere. We had previously performed this integral, epsilon naught times E dot dA. We had previously performed that integral in the case of a sphere, and we'd gotten the result Q. But now, what is it that we can expect to get? The second electric question will be very similar. I'm going to have, once again, my favorite peanut shape. Oh, here, I'll draw the peanut so we're integrating over that. Here I've got my favorite peanut shape. And again, I'm going to ask about this integral, epsilon naught E dot dA. But in this case, the point charge is going to be sitting somewhere outside the surface. There, like so. And I want to know what I can expect for that integral. And then finally, in a knowledge across, when I integrate over the peanut. And then finally, for just as we had done before, I will have a peanut-shaped surface, like so, And now I'll have charges Q1, Q2, and Q3 will be inside the surface, and Q4 and Q5 here will be outside the surface, and I'm going to inquire when I do a closed surface integral of epsilon naught times the electric field around that peanut-shaped surface, what is it that I should expect to get? Well, let's begin to answer these questions. The way we've been trained now to answer this question is, well, I would go directly to my fluid analogy. In the fluid analogy, I'm just integrating J.dA, and I know the result that I'd gotten previously. It was just the current that was being pumped into the system. But by our translation table, remember that those currents just correspond exactly to the specific charges. So in this case, I expect also to get just Q. It doesn't matter what the shape is. So this is also independent of shape. A very important result for electric fields. The next scenario, this is where the charge was outside the surface. Well, you can see how this is going to go. It's outside the surface, so there will be electric fields coming outward from that particular charge, but they're going to go into the surface on this side, say, which would make minus contributions as they go in there. And they will be coming out the back of the surface where they will be making positive contributions, and those contributions will cancel out. And we can do it again by analogy. You go to water world, you're looking for the net current flowing through this thing. In water world, you got 0. And because the velocity field in water world is exactly the electric field in electric world, you also just get 0 for this particular case. In our third and final example, what you see is, again, I think it should be clear what we're going to get. The outside charges act just like outside fluid sources. They don't contribute to the net flow out of the surface. What does contribute are, in the water world, it would be the point sources that are inside. In the electric world, it is just the corresponding quantity, the charges, which are on the inside. So this would just give me Q1 plus Q2 plus Q3. Very good. So if you've followed the discussion so far, you've actually, and were able to guess while I was discussing things, this particular result. What you've done is you've actually, in your own mind, put together this new very powerful physical law that I've been trying to prove to you, and that is something known then as Gauss's law. So I'm going to put that in a box over here and just make the general statement. So Gauss's law says the following, and this is how it is usually written. Gauss's law says that if I were to integrate the electric field around any closed surface, E.dA for any surface, and I'll just, draw some strange, peanut-shaped surface here, but it's any surface, of course, that it works for. What you get when you do that integral is equal to just the sum of the charges which are inside your surface. Now, one thing I want to emphasize, you'll notice it might look like I accidentally dropped my epsilon naught, but that was no accident. When we write down Gauss's law, for historical reasons, what we usually do is just divide both sides of this equation by epsilon naught. So here, maybe I'll just do that here mathematically. I could divide by epsilon naught and divide by epsilon naught so that the epsilon naughts cancel out and you just have integral E.dA, and what it equals then is the sum of the charges which are enclosed in the surface. That's usually denoted as capital Q to indicate a total sum. It's given as subscript ENCL, meaning the enclosed surface, the charges that only exist in the closed surface, and then because we've divided by epsilon naught, there is divide by epsilon naught. And that is a very general rule of physics, which we shall be investigating the consequences of coming up in just a moment. The last little thing I'll mention is that this integral, because it's basically measuring, in water world at least, the outgoing flow or outgoing flux, this integral is often called capital phi. That's corresponding to the Greek letter F. And so capital phi stands for flux, and we frequently give a subscript E because we're measuring the flux associated in this analogy with the electric field. Later we'll be looking at magnetic fluxes, so we keep that subscript. And that's our final representation then for Gauss's law.